Right, this is the fourth video for Module 13. We've talked a lot about the structure of an atom and all the parts of an atom. So now we're going to get into the strong force, since now we have a basis for understanding where the strong force is taking place. All right, so let's talk about the strong force. I've already told you that strong force happens inside the nucleus of an atom. We will call it a nuclear force, a strong nuclear force, because it is overcoming the electromagnetic force that wants to push the protons away from one another, since they are positive. It is taking place only inside the nucleus of an atom. It has to be at very, very close contact for the strong force to take place. It can only be taking place inside the nucleus of our atom. It is what holds the nucleus of the atom together. And if you think about it, since everything is made up of atoms, the strong force is what holds everything together. So it was said in church one time, it was really, really interesting. It was just kind of an aha moment for me. That strong force that's happening, that is holding things together, if that strong force wasn't there, atoms wouldn't exist. And if atoms didn't exist, we wouldn't exist. Well, who created the atoms? Who created it so that there would be a force between them, holding them together? Well, the Creator did. And the New Testament tells us how Jesus is the Creator. And then it says that by the word of his mouth, he created everything. And I love Colossians 1:17. It's one of my favorite verses, probably because it has to do with this and it has to do with physics, but it's very neat. So it just says that he is before all things, and in him all things hold together. Well, that is the strong force. Jesus is the strong nuclear force that is holding us all together and forcing those protons to be together to allow atoms to exist, to allow us to exist. And so not only did he create us, he holds us together and he saves us and sustains us. It's just really, really cool. All right, so what scientists think happens inside there in order for this strong force to exist? I would say it's Jesus, but they have to look for another reason. Protons and neutrons have an exchange going on called pions. They are exchanging these little tiny particles called pions. If you'll recall back to when we were talking about gravity and the theories of why gravity exists, one of the theories was the graviton theory. And the graviton theory said that they thought that the reason gravity exists is because all objects are exchanging these gravitons, and that you exchange it better when you're closer together, and that's why gravity is stronger when you're closer together. And they thought that there wasn't a whole lot of proof for this, except for the fact that there are other forces where they've got some evidence that show that smaller particles are being exchanged. Well, that's what's going on between the strong force and the weak force, is that is that particles are being exchanged. And there's quite a bit of evidence to support that this could be going on. So they've called the little particles that protons and neutrons exchange, they call them pions. Pions are very, very tiny, and they are very short-lived, and that is why the protons all have to be close enough together, because the closer they are, the better they are at exchanging these pions. And so the pion exchange has to be done very quickly, because pions are going to die very quickly. So I've also talked about how protons and neutrons are not the smallest particles. The protons and neutrons are made of smaller particles, and what they're made of are called quarks. And so within each proton, the little quarks that make up the proton are exchanging something as well. They believe they are exchanging something that we would call gluons. So these particle exchanges are the center of what scientists would say the strong force is, although I would say the strong force is just Jesus holding us all together. So we've also talked about radioactivity and how when you have an isotope, if you have too many neutrons added or too few neutrons in an atom, it becomes unstable and it becomes radioactive. So radioactivity is governed by the weak force. So we have gravity, we've talked about. We have electromagnetic, which we've talked about. Strong force, which we've talked about inside the atom, inside the nucleus of each atom. And then when you have radioactivity going on, that is governed by the weak force. So radioactivity is the result of radioactive isotopes. And what is actually happening is that those isotopes, the nucleus is not stable, specifically those neutrons. When you get too many unstable neutrons inside your nucleus, then your nucleus is not stable and it wants to break apart. And that is radioactivity. So when it breaks apart, then you change the isotope completely. So if an atom is not stable, The nucleus wants to decay in order to become stable. Okay, so that decay is radioactive decay. That is when your neutrons are losing parts of themselves in order to become stable so they can be normal. All right. So the first type of decay that we're going to talk about is beta decay. Now, what's really going to be important is that you be able to tell the difference between these decays, explain what's happening in the decay, be able to identify what the daughter product will be when a radioactive decay happens, as well as ways to protect yourself from each of these types of radioactive decays. So it's super important and it's really complicated, so make sure you take good notes. All right, so beta decay. When your neutron that is unstable changes and becomes a proton, and then it just sends its electron out. So remember we said that a neutron is made of a proton plus an electron plus an antineutrino, right? So beta decay, that neutron breaks down, it becomes a proton, and it shoots your electron out altogether. All right? So basically what happens is you have a completely different atom. Remember, if we change the number of protons, we change the atom altogether. If we go from 5 to 6, we change it altogether. So when we have beta decay, we get a completely different atom that has one more proton. It's going to have the same mass. It just has a different proton. It has a new proton. All right? So the radioactive isotope, the neutron changes into a proton and the atom changes to the daughter product, and then it sends out that electron. This right here is your beta particle. All right, so let's say we had uranium-239. Remember, that is your atomic mass. And if we write it like that, that is your mass right there. If we had uranium-239, that is definitely radioactive isotope. If it spits out a beta particle, what you have left with is a new, completely different atom. New, completely different atom, same mass. If you're looking at it on your periodic table, so they pretty much go up in number, right? So you go, let me see what uranium is. The atomic number for uranium is 92. So NP is 93, and then after NP is PU. Whoops. So what happens is our neutron becomes a proton, which changes our atomic number and makes us shift upward. So beta decay, we're going to shift upward by one spot, keep the same mass. Right, so we did beta decay. Let's look at alpha decay. So just like in beta decay, we add a proton, right? Keep the same mass. For alpha decay, it's something completely different. You take your nucleus and you actually throw out an alpha particle, and an alpha particle is 2 protons and 2 neutrons. It's basically the helium atom nucleus. So you've got your nucleus here, and you're going to shoot out 2 protons and 2 neutrons. Well, what is the mass of our helium nucleus that we're shooting out? We are losing 4 in our mass. So beta decay, you keep your mass. Alpha decay, you decrease your mass by 4. So let's look at this one. So let's say we're starting out with polonium 214. It has a atomic number of 84. We are getting rid of 2 protons and 2 neutrons, which changes it completely. It changes it into lead. And then we take our mass of 214, subtract 4 for our helium, and we get a 210. So the reason the mass changes on this one, it doesn't change on beta. On beta decay, all we're really shooting out is our electron. We keep our proton with it and we shoot out the electron. The electron doesn't really affect our mass at all. Only the protons and neutrons affect the mass. The reason this changes the mass is because we have a whole helium atom that's leaving. We have 2 protons and 2 neutrons that are leaving, which causes us to have a decrease in mass. So if we're looking at it on our periodic table, we've got our lead here, which is atomic number of 82. Next to it is Bi, and it has an atomic number of 81. And then we have our Po, which is an atomic number of 83. All right. So we're starting from here. If it's alpha decay, we're going to go back 2 spots because we lose 2 protons. And then we adjust our mass by 4. Okay, so we have beta decay, where we gain a proton, keep mass. Alpha decay, where we lose 2 protons and lose a mass of 4. The third one is called gamma decay. So when you have a particle that is degrading due to gamma decay, it emits a gamma ray, which is just a high energy photon. So it spits out a whole bunch of energy. The isotope doesn't change at all, and the mass doesn't change. There's no protons coming or going. There's no mass coming or going. The isotope stays the same. So if we had thorium-229, which remember this is our atomic mass, if it shoots out this photon, this gamma ray, then we end up still with thorium-229, but it is more stable. So let's practice one. What is the daughter product that results from the beta decay of SR90? So first we're going to need to look that up in our periodic table. Give me a second to find it. All right, so I'm going to draw you a picture of what is around SR90. So it has an atomic number of 38. On this side is, RB. And on this side is Y39. So remember, beta decay, we are gaining a proton. So we'd actually move forward 1. And the mass doesn't change. So we would end up with Y90. So what is the product of alpha decay of 241 AM? So since it's alpha decay, that is a helium atom, we're going to go back 2 spots. We need to know this over here. So AM All right, so AM has an atomic number of 95. Next to it is Pu of 94 and NP 93. So alpha decay, we're going to go back 2 spots. So our daughter product is NP, and then we're going to take our 241, subtract 4 from it. So it would give me a 237. Click on the link, complete the quiz, and I will see you in class.